In this video, I want to go over bond angles and covalent molecules. I'll go over what they are, how they can be predicted, why they're important, and how they can be used chemically. First, let's look at what bond angles are in a covalent molecule. Bond angles in a covalent molecule are exactly what they sound like they would be. They're the angles of the bonds that are in the molecule. There are three main types. There's a linear angle, there's a trigonal planar, and there's an angle that is tetrahedral. This is a hydrocarbon, it's methane, and it has a tetrahedral geometric shape. So with this shape, if we take any of the hydrogens on the outside and measure from one to the other, it will be 109.5 degrees. If we took this hydrogen and measured the angle between this hydrogen and this hydrogen, it would be 109.5 degrees. We could also take this hydrogen and measure the angle, and it would be 109.5 degrees. And we could do that with any of the hydrogens with the tetrahedral geometric geometry. In a previous video, we did resonance structures, and we used the carbonate ion, and that molecule had the trigonal planar shape. In between any of these oxygens, whether it's between this oxygen and this oxygen or this oxygen and this oxygen, should have an angle of 120 degrees or close to it. If there's a double bond, one atom may skew a couple degrees, but generally the trigonal planar is 120 degrees. Looking at a molecule that's 180 degrees, we have carbon dioxide. This is a molecule that we also did in a previous video, which is also known as a linear molecule. So now the question becomes, how do we predict the bond angles in covalent molecules? We can predict bond angles in molecules by using the valence shell electron pair repulsion model. Before we get into that, let's take a look at the structure of an atom. An atom has a center nucleus, which has a positive proton, and a neutrally charged neutron that's in the center. And in the outside of the atom, we have the electrons, which are negatively charged. So if we have two atoms, atom A and atom B, the electrons on the outside of the atom that are negatively charged, the valence electrons, the outermost electrons on the atom, are going to repel the outermost electrons on atom B because they both have a negative charge. So now we know that the valence electrons from one atom will repel the valence electrons from another atom, and they'll want to get as far away from each other as they can possibly get. And through that reasoning, we can predict what shape the molecule will take on. Let's use the hydrocarbon methane as an example. Methane has a formula of CH4. We can put carbon in the center, and the hydrogens would be around the carbon. In order for the valence electrons for the hydrogens to be as far away from each other as they possibly can, the methane molecule would have to take on the shape of a tetrahedron. So this hydrogen is coming out of the screen, this hydrogen is going into the screen, and these two hydrogens be on the plane of the computer screen. Let's take a look at the carbonate ion and carbon dioxide. So in order for the oxygens on the carbonate ion to be as far away as they possibly can be, they have to take on a trigonal planar shape, and the bonds would be 120 degrees apart. We determine that carbon dioxide has a Lewis structure like this. You can see that the bond angle is 180 degrees. Once we determine the bond angle and the shape of a molecule, we can then determine some of the properties that that molecule may take on. Let's take a look at water, carbon dioxide, and methane. As we can see, carbon dioxide has a linear shape of 180 degrees. Methane has a tetrahedral shape of 109.5 degrees. Water is a bit different. It has a bond angle of 104.5 degrees, and that's because these two lone pair of electrons on the oxygen atom repel the electrons on the hydrogen atoms. This makes the water take on more of a tetrahedron shape. This slight difference a water molecule has of 104.5 degrees gives it some unique properties that most other molecules don't have. One of these properties is when water goes from a liquid to a solid, the volume actually increases, where most other molecules, the volume will decrease. And the increase in volume makes the solid form of water less dense than the liquid form of water, which is why ice floats on water. This unique angle that water has of 104.5 degrees is very important. If water took more of a tetrahedron shape, where the bond angles were 109.5 degrees apart, or if water had a more linear shape where the bond angles are 180 degrees apart, water would be very different than what we are used to. For example, if water was more linear, it may be a gas at room temperature instead of a liquid. Now let's take a look at how the shapes of molecules can be used in chemistry after they're determined. The shape of a molecule and the bond angles that it has can have a very big influence on the stability of the molecule and the reactivity it has with other molecules.